quantum permutation. Yeah, and then the A is just got to be non-zero, so small enough to make.
Next topic is Jason on matrix K. Thank you for inviting me. It's a pleasure to be here. So I'm going to talk about some topics-based joint work with Jonathan Reed, who is now in Toronto, and Philippe Ridelet, who's So this is going to be about two classical problems, matrix scaling and optimal transform. And these problems I think are ostensibly seem a little different, but actually there's some pretty deep connections and some nice things that go on between them. These problems have a number of applications, which I'll mention shortly, and there's some practical algorithms which people use, have been using for a long time, but the theoretical guarantees were not kind of fully understood. So I'll try to talk about this, and along the way hopefully shed some insight into the problems and the connections between the two. So the first problem to talk about is matrix scaling. This is a very classical problem, which some people in the room have worked on. So I'll talk about applications in just a second. Actually, I think you guys maybe have heard about something related to this problem yesterday. I couldn't attend because I couldn't escape my teaching duties, but I'll just review the basics so we're on the same page. So what is this problem? It's an algorithmic problem where you're given, let's say, a non-negative matrix. Actually, for simplicity, you can have a strictly positive matrix, n by n, so its entries are strictly positive. You're also given two distributions, and probability distributions. We'll call them R and C. So these are things in the simplex. So simplex is just all vectors, non-negative, whose sum to 1. And the task is to find, so the task is to find diagonal matrices, in fact positive diagonal matrices, x and y, such that this scaling matrix, xay, satisfies something I'll write in a second. So what is going on here? When you multiply by a diagonal matrix on the left, you scale the rows. You multiply by diagonal matrix on the right, you scale the columns. I'll have an example to be super concrete just in a second, but so you're allowed to scale the rows and columns, and you're asked to find such a scaling such that the rows of B equal R and the columns of B equals C when you sum. So I'll write this here. You want the row sums of B to be R. Here the row sums, this means if you want matrix multiplications, B times 1. So the first entry of this is summing up all the entries in the first row. The second entry in this vector is summing up all the entries in the second row, and so on. And you also want the same thing with the columns. So this here is matrix multiplications, B transpose times 1. So in kind of the picture here, the geometric picture, and the vocabulary some of you guys might use is you look at this matrix A, and you look at the orbit formed when you look at the group action of pre and post multiplying by diagonal matrices. And you're asking to find, so that's what this curve would be, all the matrices of that form, and you're asking to find such a matrix that has certain row sums and column sums. These are affine constraints. So in other words, you're asking if there's an intersection of this orbit with a certain affine subspace. Okay, and you want to find such a point at the intersection.
So could you repeat this? What does it mean that rows of B are correspond to the distribution R?
Okay, so if B is equal to 1, 2, 3, 4, oh, that's not distribution. Let's do 1 quarter, 2 quarters, and so on. The row sum, the first entry in the row sum would be 1 quarter plus 2 quarters, which I guess would be 3 quarters. So the row sum is just R of B is a vector where you sum up the rows. First entry is, thank you. Yeah. So it's B times 1 if you like. Okay, so let's give an example. So consider the matrix A, which is 1/2, 1/4, 1 and 1/16. And I give you also these row and column marginals. R is equal to 3/8, 5/8. C is equal to 5/8, 3/8. So this is a valid input because A is a strictly positive matrix. These are distributions, they add to 1. And turns out there's a certain scaling. So this will be the matrix X. This will be the matrix Y. This is my these this is X, this is Y. And if you write this out, it's equal to 1/8, 1/4, 1/2, 1/8. And such a matrix is scaled appropriately. Because if you add up the rows, the first row adds up to 3/8, the second row adds up to 5/8. This is exactly R. The columns add up to 3/8. Oh, hold on. Second, 5/8, and 3/8, which is exactly C. So this would be such as a valid scaling for our given matrix A and R. Okay, so a couple of actual questions. First, does such a scaling always exist? And here I exhibited a certain valid scaling. If it exists, is it unique? And also, can you find it? So I'll talk about these things in detail in just a second, but perhaps if this rings a bell, it's something called Sinkhorn's theorem, which guarantees these things actually happen. Before I talk about details, let me mention a couple applications where people care about this. This problem has been studied in a number of different communities. One is scientific computing, and the main idea here is this is very useful as a preconditioning subroutine. So in scientific computing or numerical linear algebra, sometimes you want to solve the system, linear system like A times U equals V. And if this matrix A is polarly conditioned, this can be difficult for numerical algorithms. And it turns out that actually if you, to solve the system, it suffices to solve this first scaling of A. And sometimes this can help conditioning a lot. Another application is approximation of the permanent. So the main idea here is that you want to compute the permanence of a strictly positive matrix A. This is a difficult problem. One really beautiful algorithm possible now is to scale the matrix A in a certain way, and kind of a key point is the permanent is multilinear, meaning that if I multiply the first row by 2, the permanent multiplies by 2. So basically, if I can compute the permanent of a scaled matrix, I can recover the permanent of the original matrix. And it turns out that if you scale such a matrix in a certain way, you have a pretty good guess at what the permanent is going to be. So anyways, it's a really nice topic, and basically scaling helps you with this approximation of permanent. My last application is optimal transport, and I'll mention this later, but this has applications in machine learning and statistics, etc. Okay, so anyways, matrix scaling, classical problem, has a number of applications, and that's not a very straight line. So now I'll talk about, yes, the question about does such a scaling exist, is it unique, and how to find it. So there's a theorem called Sinkhorn's theorem that actually a scaling always exists, and is essentially unique. I'll put unique in quotes. So unique in the sense that if I multiply this matrix X times 2, I can divide Y by 2, I get the same thing. So up to this multiplication and division by a scalar, these matrices are unique. Okay, I should mention here a remark that I'm purposely hiding some details on the rug. The reason why scaling exists and you have this nice theorem is because I'm assuming that the matrix A is strictly positive. There's some very beautiful result which is more detailed about if this is possible when the matrix is not just strictly positive but non-negative. And let me just quickly give some examples. So in this picture I drew here, so again you look at this orbit and you look at this subspace. So in the example here you had an intersection, right? And this theorem says that if matrix A is strictly positive, you always have a picture like this. There's also two other pictures. One is that you're very far actually, there's no intersection. If A has can possibly have 0 entries. So example is if A is equal to 0, 0, 0, 1, there's no way to scale this in such a way that, for example, the row sums add up to 1/2. Because no matter how you scale it, these two things go up to 0. So here, you cannot scale at all. There's also an intermediate situation where there is no intersection, but it gets arbitrarily close. So this is sometimes called approximate or almost scalable. And a good example is matrix 1, 1, 0, 1. If I want to scale this to be doubly stochastic, so if I want the rows to add up to 1/2, 1/2, 1/2, 1/2. Turns out there's a certain scaling. So if this is A, there's a certain scaling where B is equal to 1/2 epsilon 1/2 0. And okay, so maybe this is a family of scalings, B sub epsilon. So this could be different points along this on this orbit, and as I take epsilon closer to 0, this becomes closer and closer to the exact scale. So there's 3 different settings in general, and there's actually a way to detect which setting you're in. This is a classical topic about kind of the sparsity pattern of A. And I won't talk about this more, but I guess I'll just mention that this can be efficiently checked with a certain max flow. So in practice, people use, I guess, there's a number of really great algorithms, but the algorithm of choice in practice for the last 50 or so years has been this algorithm called Sinkhorn's algorithm. It goes under a couple names, sometimes also alternate minimization, sometimes also the RAS method. I'll just call it Sinkhorn scaling today. And it's a very simple algorithm. What it does is it alternately corrects the rows and then the columns. So if your matrix A, has some stuff here, I need the rows to add something, and I need the columns to add something. What the Sinkhorn algorithm does, it's an iterative algorithm. You start with the current matrix, and you repeatedly scale it, and so it gets closer and closer. And what you do is, first, these rows have something wrong, and so I'll change the matrix X to make these rows add up correctly. So these will now be correct. In doing so, I may mess up the columns. So then I try to correct the columns by changing the matrix Y on the other side. This messes up the rows. And so you keep on going back and forth, and you hope that somehow this converges. So it turns out it does converge. And it converges actually quite quickly. One issue is if you try to actually prove that it converges quickly, I guess the natural question is how do you measure progress? Because in every iteration, you fix one side, but you screw up the other. So I guess people have been using this in practice for a long time. It works really quickly. In just a few iterations, it seems to converge to as much area as people need, and it's implemented in many commercial software packages. But the theoretical guarantees were not very well understood. How fast an actual bound on how many iterations you need. So today I'll try to give you, I'll talk about actually a theorem that says this converges very quickly. In fact, you need very few iterations. A number of iterations is essentially independent of the size of the matrix. That will be the main result. Of course, this algorithm doesn't converge in general after a finite number of steps. It gets closer and closer. So if I want to say that you're good enough after a certain number of iterations, I have to say what it means to be approximately good enough. There's a number of ways to measure their distance. So in the picture, I'm just saying that maybe it won't converge to this point. Maybe I'll get closer and closer and closer, and I have to somehow say that after a couple steps, I'm close enough. I'm close enough to the point I want to get to. So the definition of, let's call it epsilon scales, meaning epsilon far away, we'll say that a matrix B, which for us will be of this form, we'll say this is epsilon scaled. And of course, when we say epsilon scaled, we mean for certain marginals R and C. So for R and C, if so to be exactly scaled, I want the rows to be exactly equal to R, and I want the columns to be exactly equal to C. Say epsilon scaled, I'm going to say that the distance in L1 is going to be small. And of course, there are a couple different ways you can measure it. This turns out to be a very natural way to measure the distance because these are probability distributions, and particularly it's actually the way that the way to measure that gives you good values for optimal transport, which I'll talk about shortly. So we'll focus on this definition. And the main result, so this is on and lead, is that if you run this Sinkhorn algorithm, scale the rows, that's one iteration, scale the columns, second iteration, and so on, then you only need a few iterations to become epsilon scaled. In particular, so Sinkhorn scaling is epsilon scaled in tilde of, all right, probably 1 over epsilon times. So this is the maximum entry of A, the minimum entry of A, this many iterations. Okay, so let me break this down. So the O tilde is hiding log factors. In fact, only one factor of log. So I'll explain kind of what these things are in a second, but kind of the key point, the key takeaway, is that the number of iterations that you need to scale the matrix is essentially independent of the size of the matrix of n, which is why this is actually going to be a nearly linear time algorithm. Because the time it takes to just read the input is n squared. Right? You have to read the full matrix, which is n by n. Each iteration can be implemented in n squared time. You basically have to sum up entries in the n by n matrix. So the total runtime of the algorithm is roughly n squared in n. In other words, this algorithm is nearly optimal in the sense that it runs in roughly the same time it takes to read the input. I can mention later, there's different things here, but that's kind of the key takeaway. And so it's the end of the day, so I won't make you sit through long proofs, but I want to give you kind of a sketch of how this is proved, because actually the proof is super simple and I think somewhat insightful. So before I say the proof, let's just develop a tiny bit of notation. So these diagonal positive matrices x and y, we're going to parameterize them as follows. So these are positive diagonal matrices. So we'll parameterize them by, I guess, sometimes people call it the exponential parameterization of the group. So just a vector, and e to the xi will be the entry. And same thing with y, so y will be equal to e to the y1, e to the yn. So what does Sinkhorn's algorithm actually do in terms of these vectors x and y? So it's a very simple iterative update. So Sinkhorn scaling. And this is exactly the same algorithm I kind of sketched with the picture but didn't actually write down, so I'll write it down now. So what do? You initialize let's say with no scaling. So I want this matrix x to be identity, y to be identity. I haven't scaled at all. That just means I let x and y be 0 vectors. And then you iteratively update. So you either update the rows or the columns. So if you update the rows, then this means you update so the current row sum, the current ith row sum of the matrix is Ri x y. That's what I'm just writing. You want it to be Ri. So if you add this, then because we're doing this e there, this makes the new row sum correct. So this is just saying you update, if you want to update the rows, you update the matrix on the left in this simple way. And if you want to do the columns, it's exactly the same thing. So now I replace x with y and rows with columns. So just to be explicit, this is, you either do this. You either do the rows or you do the columns, depending on, whether the iteration is odd or even. Okay. So I want to prove that this converges, meaning you're excellent scaled in few iterations. And the key idea will be to measure progress in a good way. Remember I said before that when you update the rows, you mess with the columns, and vice versa. So you want to somehow be able to say that I'm actually always making progress. And we'll do this with a certain potential function, which is very intimately related to matrix scaling. So this is a function over x and y in Rn. And there's kind of two observations. So one is that minimizing phi corresponds to scaling the matrix, to optimal scalings. So I'll just write the scaling. In other words, if I'm given a matrix scaling input of the matrix A and the marginals R and C, then I can form this corresponding function. If I minimize this function, I find the optimal little x, little y, then the corresponding matrices big X, big Y give me the optimal scaling. And also, moreover, an approximate version of this holds. So if I approximately minimize phi, I also approximately scale the matrix. Because I'm just going to be trying to be approximately scaling, that means I only have to approximately minimize this function. Yes?
So, just because I've seen something that looks a lot like this, but it had a
This is
log.
like classical, this is been used in connection matrix design for like 20, 30 more years.
It usually has a log in front of the sum.
This version does not. I can talk about that offline.
Is A already normalized or something? All right.
It doesn't matter.
It doesn't matter. Okay. All right. Yeah, go.
So, my second observation is that Sinkhorn scaling. So I want to relate this problem of matrix scaling to minimizing this function phi. I've told you that minimizing the function is the same as scaling, but also the algorithms kind of correspond. So sequence scaling is nothing for matrix scaling. This is exactly the same as if you're an optimization person, what's called block coordinate descent on phi. I won't get too detailed on this because it's not very important, so if you don't know what block coordinate descent is, you can ignore this for a second. But basically, there's a certain, this is a convex function, there's a certain way of optimizing convex functions by fixing x and then solving exactly for y, and then fixing y and solving exactly for x, and going back and forth. This is exactly what Sinkhorn's algorithm does on the big matrices x and y. So, what to erase? Let me keep this definition and the theorem. Probably could have chosen better where to write these. And I will try to prove everything in just the upper space. So the proof in a picture. Is I want to somehow, again, I want to show this, I only need a few iterations. And I'm going to prove this with a potential argument. So let's say, so this is phi star. This is the optimal value after we've minimized over x and y. And this is the value when x and y are initialized, so at the very beginning of the algorithm. There's going to be two key lemmas in this proof. One is that after an iteration of Sinkhorn, I make a lot of progress. I get much closer to optimal. So that's lemma 1. It says that each iteration makes a lot of progress. A lot of progress. And then the second lemma is that I don't have to make a lot of progress when I start, so that the gap is pretty small. So lemma 2 says, don't have to go far. So quantitatively, so lemma 1 says that if I'm at current scaling, let's say, called x and y, and I update to a new point, so I do one iteration of Sinkhorn, call it x prime, y prime. In fact, only one of them changes. Let's, for simplicity, say I'm doing a row update. So only x changes and y doesn't change. And this says that I move far in this iteration. Somehow my potential drops a lot. That's exactly what we're going to write. We're going to write that the potential of the old point minus the potential of the big point, or the new point, is large. And in fact, we can quantify this by the what's called the scale divergence between, get the order right, between the rows I want and my current rows. So this is for a row update. For a column update, it would be exactly the same. I change y instead, and I do the columns instead of rows. So, okay, actually, I will need more space. What to erase? Let's erase.
Maybe the definition of epsilon's good.
Okay. So just as a reminder, the scale divergence. Okay, so let's do this side. The definition of scale divergence between two probability distributions is this thing pi log pi over qi. Very important notion in statistics, information theory, etc. One important fact about it is that what's called Pinskers inequality, which says that the scale divergence between two distributions is at least the L1 distance squared over 2. And we'll use this next time. Okay, so that was lemma 1, you make a lot of progress in each step. Lemma 2 says you don't have to go far. So lemma 2 says that the gap between the initial value and the optimal is relatively small. And in particular, it's less than roughly the maximum value of A over the minimum value of A at the initial plot. Okay, so ideally, I'd prove each of these lemmas and tell you how they also apply to the final statement. For sake of time, let me skip lemma 2, because this is something that's actually pretty classical and pretty much follows from the definition of phi. Let me just show you the proof of lemma 1 to this one line, and also how these two imply the theorem, because that's also essentially one line. So let's do this. The proof of lemma 1. So let's write what this is, just in terms of definition of phi. So you have sum of aij dxi j minus rx minus cy. This is the potential for xy. And then you subtract the potential for exactly the same thing, but now you have a prime on xi and a prime on x. Y has not changed, so these things are exactly the same, they cancel. These sums are actually both 1. Why is that? Because in each iteration of Sinkhorn, either your rows are normalized or your columns are normalized. This is exactly the sum of all entries in the matrix. So it's in particular equal to the sum of everything in the rows or everything in the columns. It's equal to 1. So these are both the same. So you're left with just these two terms, which is Rx prime minus x. Now we look, what's the definition of x prime? So x prime is the new point. So the new point is exactly the old point plus this extra log thing. So just plugging in the definition of what Sinkhorn does, what the new point is, this is sum of Ri times this sub I. So exactly log Ri over Ri of xay, which is exactly the KL divergence. So this is kind of just follows from, if you have the right potential function, you can measure the improvement potential in a very natural way. And you know, this is nice because it says if I'm not close to being scaled, if these two things which should be equal are very far from equal, then actually my progress is big. Okay, and the last thing I'll do is say, for scaling, is say how these two lemmas imply the final statement. So, okay, now I no longer need this. Ooh. So now the proof of the theorem. So I'm trying to argue that you don't need many iterations to converge. So say you have not converged yet. So if not yet epsilon scaled, this means, if you remember the definition I erased, either the rows are far in L1 or the columns are far in L1. Right? Because one of them is always 0. So let's just pretend it's the rows that are far. So this means that so the rows are far. And this is the definition of not being epsilon scaled. So now we use lemma 1. So lemma 1 says that the improvement in the potential in this next iteration is equal to this KL between the two, which by Pinsker's inequality is at least the L1 distance between the two, up to a factor of 2, and this is at least epsilon squared. So in other words, if you have not yet converged, then an iteration of Sinkhorn improves your, makes this gap at least epsilon squared. And since lemma 2 says that this gap is not very large, you can't drop down too many times. Particularly, the most amount of iterations you can do is the gap divided by epsilon squared, which is exactly what this is. So in fact, this is, you can make this 1 over epsilon squared. So that's more or less the proof sketch. Are there any questions?
Could you say where the login comes from?
Okay, the login comes from this thing. So there's a more refined bound where this is actually the sum of all the entries of A over the minimum. And a very crude bound is bound this by n squared times max over min, and take the 1 log into here. Okay, should I stop at 5? I started a little bit late.
You can take 5 minutes.
5 minutes? Okay, thank you. So let me just conclude this part about matrix scaling very quickly. So just want to, there's some details in here, some calculations, but just the main point is there's this algorithm, Sinkhorn scaling, for this problem, which has been used a long time in practice, converges in very few iterations, and kind of the main result was that actually this is provable. You only need very few iterations to converge. I should mention there's a lot of other work on matrix scaling. So it turns out actually in the beginning you make actually a lot of progress, and then this epsilon squared becomes tight. So you can actually even improve this 1 over epsilon squared to 1 over epsilon. This is follow-up work by 3 people, B, G, K, and T, to make this 1 over epsilon squared. There's also a lot of more sophisticated techniques for matrix scaling by some people in the room, which operate in the way, remember I said that matrix scaling is the same as minimizing this function. So if you just think about this as a convex optimization problem and try to plug in your favorite convex optimization algorithms, and some very sophisticated techniques for doing that. These require Laplacian solvers, so are not currently implementable, but I think are a really nice theoretical benchmark. And so what these let you do is get a kind of log 1 over epsilon. So hopefully those can be implementable at some point. So in the last couple of minutes, let me mention the second problem, which is optimal transport, and just very briefly mention some connections. And kind of one point I'll try to make is that these fast algorithms for matrix scaling actually also give you fast algorithms for optimal transport. So what is this problem? You've probably heard about it in like intro to CS courses or operations research if you've been taught it before. A classical setup is you have a company, and the company has some factories. So this is one factory, another factory, another factory. And you also have some stores. 1 store, 2 store, 3 stores. The factories, let's say this factory makes 40% of the widgets your company sells. This one makes 30%, and the other 30%. And over here, maybe 40%, 10%, 50%. Meaning that this is the number of widgets that store is going to sell. You also have costs between every pair of factories, between factory I and store J. You have a certain cost of transporting a single widget. And the question is the following. How should you transport widgets from factories to stores such that for every factory you transport all the widgets? For all the stores you get exactly the amount of widgets you want, and you minimize your total shipping cost. Mathematically, this is just a linear program. So this is minimizing over the amount, I'll call Pij the amount that I ship between factory I and store J. So you minimize P. This tells you how much ship. Your cost is the total shipping cost. And you have 2 constraints. One is that all the factory demands or factory supplies are met, so that the rows of P equal R. And the second is that the demands are met, so the columns of P equal C. Okay? So this is a linear program because both the objective and the constraints are linear in decision variable P. Mentioned briefly that this is a kind of very fundamental problem in probability theory and analysis because it gives you a natural way to lift distance between points to distance between probability distributions. It's used a lot in statistics and data science because it gives you a way to measure distances between data distributions in a way that respects the underlying geometry of the data. It's also used in graphics and vision, gives you a way to interpolate between shapes, between colors and textures, etc. So people have, there's a long line of work on these problems. Just very briefly, one algorithm is Hungarian algorithm, which actually dates back to the 1800s, and it solves this problem in n cubed time. Sorry, n is the number, well, pretend there's n stores and n factories. So it solves this problem exactly in n cubed time. Because it's a linear program, you can also use off-the-shelf linear program solvers, and using the best ones right now, you can do this in roughly n to the 2.5 time. Not currently implementable, but still a nice theoretical benchmark. And it turns out with this matrix scaling algorithm, you can actually solve this. So the reduction of matrix scaling, I'll just sketch. You can solve this in n squared time. And this will do something approximate. So what it'll do is it'll give you a shipping plan, so P, for which the cost is within epsilon, so plus or minus epsilon of the optimal. And you can, to get that kind of a solution, an approximate solution, takes you roughly n squared time. And again, this is nearly optimal in the sense that to even read the input, you have to read all the costs. You have n squared cost between n to n points. And this runs in roughly the amount of time. So the time it takes to run this algorithm is roughly the amount of time it takes to read the input. So it's getting late, so I'm not going to write anything more. I'll just mention that I'll write 1, 2, 3, 4 characters. If you change this program and add 1, 2, 3, okay, hold on. Depends if I should have my strokes. So if you regularize this problem in a certain way, and I guess I can talk about this offline if people are interested, but there's a certain way of changing this program, kind of smoothing it so it's easier to solve the convex optimization. And it turns out like the key message is that if you solve this problem instead, so if you solve this slightly different problem, it's good enough to solve the original problem. So, fact 1. Fact 2 is solving this problem is equivalent to solving matrix scaling, the problem I talked about before. So if you use the algorithm for matrix scaling, you can solve this approximate problem. That's good enough for the original problem. And that's kind of the main idea. All right, I should probably end. Yes?
Another way you could try to attack the matrix scaling problem is if you looked at all the weights, let's call them WIJs, so that if you look at the matrix whose ijth entry is aij times WIJ.
What is WIJ right now? Sorry.
Just a set of non-negative numbers.
Okay, and you're optimizing over those?
So first you'd like to find WIJs so that when you look at the matrix aij times WIJ, that's the ijth entry, it satisfies the row and column condition. Then the W's that do that is a nice convex set. And by Sinkhorn's result, there's a unique rank 1 matrix in that set. So is there some way to first figure out the WIJ set and then do a search on minimizing the rank of things in your convex set?
Okay, I see your question.
Has anybody tried that approach to see if they can get faster algorithms?
I have not heard anyone trying that. I would imagine the problem is exactly the problem that you mentioned, which is that in general, so you can solve over the W's that I mentioned very quickly, because it's a complex problem.
But then finding the rank 1 is
exactly, it's exactly this problem of, you could find a W which is very high ranking, most likely projecting onto a rank 1 solution will lose you a lot. But I don't know off the top of my head.
Yeah, but it's very strange because it's a convex set, so it's got lots of extreme points. But where's this rank 1? It's usually when you take convex combinations of extreme points, your rank is going up. So you would. Anyways, just wanted to throw that out as a possible alternative.
That's a good question.
So usually, sometimes in the literature, you measure the error in L2, so you're measuring the error in L1.
Yes, so L1 is stronger than L2. I mean, they're different, right? So,
They're different.
if the number of iterations to get an L1 error is, that'll also give you, that iteration will also give you an L2 error of epsilon. The reason we focus on L1 versus L2 here is for a couple of reasons. One is the L1 error is actually the error you need to get it down here. The L2 error doesn't give you anything. The other thing is between distributions, L2 error is not always very decipherable. For example, if you look at this as one vector, so call this R, and this is, you have n of monobrands and n of zeros. And I look at C, which is exactly the opposite. So you'd imagine, if I just ask you intuitively, are these vectors close or far? I mean, of course, you have to tell me what close or far means, but it's reasonable to say maybe these are somewhat far from each other. The L1 distance is indeed of size roughly 1. The L2 distance is, I think, scaling in 1 over Anderson, or square root. But it's becoming very small, actually, as it decreases. So what this is all to say is that if you think these vectors are very different, you may want to use L1 instead of L2 to measure the error, because if these are the marginals, imagine this is R and R prime. If these are the marginals I want, and Sinkhorn actually give me this, if I was measuring stuff in L2, I would say I'm done at this point. Whereas you actually might want these to be much closer.
Right, but yeah, I mean, in terms of L2 error, the already analysis of the kind of theorem I proved, for example, LSW.
Yes, but when you exactly this issue of when you change between L2 to L1, you get an extra factor of n. So the number of the iteration bound I had was something like roughly independent of n. And when you use that bound and then change from L2 to L1, you get a factor of n, which unfortunately kills the story if I want to say that I have a near linear time algorithm. Because then the algorithm becomes, if I multiply by n squared, which is the time per iteration, it becomes n cubed as opposed to n squared. This is near linear, this is not. So that's exactly the game we're trying to play.
More questions?
I mean, I guess the part of the issue with that is it's sort of not near linear in epsilon. So when you change norms, you don't preserve at all whether it's near linear or not.
That's totally true. So Raphael's algorithm gets a log 1 over epsilon. So it's good in that sense. But you lose some other things. For example, it requires Gaussian solvers, which are not commensable. So one of the purposes of this work, I guess, was to analyze a very simple practical algorithm that's used a lot in practice.
Okay, let's thank Jason again. Yeah, I think